So the next application of Maxwell's thermodynamic relation is that we can use these relations to find difference between two specific heats Cp and Cv. So as you know, Cp is the specific heat at constant pressure and Cv is the specific heat at constant volume. Now there are three different expressions for Cp and Cv, that is Cp minus Cv. Okay, so we'll determine their value one by one. The first one is this one, where Cp minus Cv is equals to T del P del T at constant V into del P del T at constant P. Okay. So now we'll prove this, show that Cp minus Cv is equal to this expression. Okay. So we'll prove this one. So we'll start like this. Let entropy is be a function of two independent variables, T and V. Okay, temperature and volume. So S is the function of T and V. Therefore, total derivative of S, which is ds, equal to del S del T at constant V into dt plus del S del V at constant T into dV. Okay. Now we will take partial derivative on both the sides with respect to temperature T with pressure constant. Okay. So now we write, now taking partial derivative on both the sides with respect to temperature T, keeping pressure constant or pressure as constant. We get, so what do we get? So on the left hand side we will have, we are taking partial derivative. So del T of S with pressure constant equal to del S del T constant V, then del T constant P plus, so here it will be partial derivative over T, temperature del T constant P, then this term del S del V constant T, then partial derivative of V del V del T at constant P. Okay. So now you see this term is 1, right? Del T by del T 1. So therefore we have del S del T at constant P equal to del S del T at constant V plus this term del S del V at constant T into this term del V del T into at constant P. Okay. So now what we will do, we will multiply both the sides by temperature T. Okay. So write multiplying both the sides by temperature T, we get, now if we multiply both the sides by temperature T, we will have On the left hand side it will be T del S del T constant P equal to T del S del T at constant V plus T del S del V constant T into del V del T at constant P. Okay. Now see, we know suppose this is equation 1. Okay, so we know that dq equals to TdS for an infinitesimal reversible process. Okay, for infinitesimal reversible process dq equals to TdS. Okay, so and we also know dq dt, okay, at constant P is Cp. So if I write also dq dt at constant P is Cp and dq dt at constant V volume is called Cv. Okay, now as dq equals to TdS, so if I write again dq equals to TdS, therefore I can also write, if I write del q, then it will be T del S. Okay, so dq equals to TdS, we are writing this del q equals to T del S. So then if I replace dq and dq by del q, so del q del T at constant P will be Cp. Okay, so instead of dq dt I am writing del q del T and del q del T at constant V will be Cv. Instead of dq dt I am writing del q del T. Okay, so now we can replace del q by T del S from this relation. Okay, we can replace del q by T del S. So T del S by del T at constant P is Cp and T del S by del T at constant V is Cv. Or finally Cp is T del S del T at constant P and Cv is T del S del T at constant B. Okay, so now we can use this two relations, Cp equals to T del S del T constant B and Cv equals to C del S del T constant V over here. Okay, to replace this one which will be Cp and to replace this one which will be Cp. Okay, so you don't need to show all these calculations. You can directly say that as Cp equals to T del S del T constant P and Cv is T del S del T constant B. Okay, so using the values of Cp and Cv in equation 1, what do we have? So this will be replaced by Cp and this term will be replaced by Cv. Okay, so we have Cp equals to Cv plus T del S del V constant T into del V del T at constant P. Okay, now we will use Maxwell's relation. So now using Maxwell's thermodynamic relation. So you don't need to say which one it is. You can just use Maxwell's thermodynamic relation to replace. So here we'll replace this term. Okay. Del S del V constant T. So according to Maxwell's thermodynamic relation, del S del V constant T is equal to which partial derivative? Now we can use the mnemonic. Okay. So remember, we go crosswise. Okay. To get the variable in this position. So from going crosswise from S, here it should be del of T, because S and T always go cross. Then del over here, which quantity will be here. So going crosswise from B, we get always P. Okay. So it is del P del T. And which at constant of what variable? So here it is V. So it will be V over here. Okay. So now the question is whether it is the positive relation or the negative relation. To find that, here if I write the mnemonic again, so S T T P, you can do this in rough. Okay, PV PV. So we know the first one and the fourth one is positive and the middle twos are negative. Now look at this. So which pair it is? So look at the variables in the denominator. So it should be the pair of SP. So which one is the SP pair? This first one is the SP pair. So it is positive. Okay. And they have a positive sign between them. So therefore it is positive. Okay. It is positive. It will remain as it is. So now using the Maxwell's thermodynamic relation, suppose this is this in equation 2. Okay. We can replace del S del V constant T by del P del T at constant V. Okay. So it becomes Cp equals to Cv plus T del P del T constant V into this term which is del V del T at constant P. Now bringing the Cv on the left hand side, we will have Cp minus Cv equals to T del P del T at constant volume V into del V del T at constant P. So this is the first expression for difference between the two specific heats Cp and Cv.